Okay, here is a basic uniformly accelerated motion problem that involves a speed skater moving across some ice. Now if we read carefully, it says there's a speed skater moving across frictionless ice at 4.9 meters per second. Hits a 3-meter wide patch of rough ice, and she steadily slows steadily, then continues at 2.7 meters per second. Alright, so apparently moving along nicely, hits some rough ice, slows down, then after the ice rough patch, she moves on at another continual speed. If I draw this out, a motion diagram, she's moving pretty steady. So, and then at this point, now she begins to decelerate. And then from that point on, moves at a constant velocity again. So these are the two places that are really important. This is where I'm going to say my x equals 0. That's x initial. My x final here will equal 3 meters, because the patch of ice was 3 meters wide. I'm going to start here at the beginning of that patch because this patch is the important part. It is during this part that I have an acceleration that I'll label acceleration 1 that is to the left. Prior to that, here the acceleration is 0. After that, the acceleration again is 0. What they were doing before this isn't really important. This phase in here is the important part. So that's going to be where my time initial is 0, and then my time final is going to happen there. Consequently, this is where I have the initial velocity of 4.9. That's during this entire phase, but all that matters is this instant. And at this instant, she's now traveling at 2.7. This is my final velocity. Right, the motion, the velocity is this way to the right. This is where she starts from. This is where she decelerates. That's where she continues afterwards. This is the phase of motion that is important. So that's going to be my beginning of time and displacement. Now the next thing I do, I only have one phase, so for that phase I'm going to list the potential variables. They'll always be the same. We'll have velocity initial, velocity final, position initial, position final, change in time, which is the difference between the time final and the time initial, and the acceleration. These same 6 values are going to be used repeatedly throughout the next 2 chapters and beyond. So we're always going to make that list. The next thing I'm going to do is see what I know from that list. What are the pieces of information? I know here's my beginning, and my velocity initial is 4.9. And I'm going to note that that's to the right. Direction is the #1 mistake you'll make. You will forget about direction or ignore direction. So I personally like putting a little arrow there to remind me of the direction. I'm going to make right positive, so this remains a positive number. Velocity final, I know that is 2.7 after hitting the ice that is rough. That is still to the right, so a positive. The initial position of my problem, I'm calling that 0. That's my choice where 0 is, and it just makes sense to begin at a position of 0. The final position is at 3 meters. So these initial and final positions must correspond to the initial and final velocity. This initial velocity must be the velocity at that position, exactly at that instant, and likewise the final at this final position. The time between this, I don't know. I put a question mark. The acceleration, I don't know. But the question is, and I don't have the question here, is What is the acceleration of the skater? Right? We want to find A. What is the acceleration of the skater? So this is what I'm finding. Now here's where I go to my list of equations that we've provided earlier in class. And I've got all these equations. These 5 equations. Now, what's valuable is this part over here. What each equation does not involve. And here, time is something that I do not know and I do not want. So I'm going to avoid this. So I look at my list. Here's the one that is not for time. That's this equation. So this equation will have everything I need, and the one thing it's missing will be the thing I want. It has the final velocity, I have that. The initial velocity, I have that. The acceleration is what I'm looking for. The initial and final positions, I have those. So that equation is going to work. So I'm going to use the not t equation, which is v final squared equals v initial squared plus 2a x final minus x initial. And that's one of the key things. Once I've drawn my diagram, identified the interval of interest, identified the variables that are valuable for that interval, then I can select the appropriate equation that gets me what I want, acceleration, while avoiding what I don't know, time. And now I'm going to rearrange this algebraically, plug in the numbers and solve. You don't have to rearrange that algebraically. But if I do, I would get this. A is going to equal v final squared minus v initial squared divided by 2 times x final minus x initial. Now that is 2.7 squared minus 4.9 squared divided by 2 times 3 minus 0. Those are all my numbers. And now I can just plug in those numbers and find my answer. Grab a calculator. And I've got 2.7 squared minus 4.9 squared. I didn't put parentheses, so I'm going to finish that out. That's the top, divided by the quantity 2 times the quantity 3 minus 0. Boom. And I get negative 2.786. Negative 2.7867. That's more digits than I need. I look up here, everything's got 2. So the acceleration is negative 2.8 meters per second squared. The question just asks for magnitude. Magnitude would be positive 2.8. Magnitude is always positive. So that's the magnitude. Oh, which you can't see in the screen, it got cut off. But the magnitude would just be this answer with out the negatives. Right? Okay, there's a problem. Sorry for the formatting, but there you go. Hope that helped. Bye.